Today, Mhairi is presenting her work, which was published at the ICLR 2023. And it's on temporal disentanglement of representation for generalisation in RL. And it's quite an interesting take on state representation learning for reinforcement learning. So it's looking forward to the presentation. Thank you for presenting today, Mhairi.
Okay, thank you for the introduction. So I guess I'll start by just introducing myself briefly, as I think there may be a few people here that don't already know me. So my name is Mhairi. I'm a third-year PhD student in Stefano's group, Autonomous Agents Research Group, here at Edinburgh. And today I'm going to be presenting temporal disentanglement of representations for improved generalisation in reinforcement learning. So as Sam mentioned, this was recently published at ICLR this year, and it's joint work with all the people pictured here on the slide in front of you. So one important challenge for RL algorithms is that they fail to generalise to unseen variations of environment variables that weren't seen during training. So this problem is especially true for image-based RL, where the observation space of the agent is image pixels. So a change in just one environment variable, such as the background color in the image, can then change many pixels in the image, which in turn can change the entire representation of the image that the agent learned in training. This means a policy based on this representation is no longer optimal after a change in the environment. So we can see an example of this in the videos here with the cart pole swing up task from DeepMind Control. On the left, we have an RL agent that's been trained to successfully swing up and balance the cart pole. However, when we change just the colors in the image on the right, the same agent is no longer able to perform the task. So often RL agents need to retrain from scratch after a simple change in the environment like this. And this failure to generalize occurs for both variables that are irrelevant to the optimal policy, such as the colors in the example here, as well as relevant variables such as goal positions in tasks where agents are trained to reach a particular goal state. So RL agents need to learn more robust representations of images that remain useful after a change in the environment. To do this, it's common to use domain randomization to maximize the variation seen during training. However, it's hard to know what you'll need to generalize to in the future, and training on every possible variation, such as all possible colors in the cart pole example here, makes it very hard for the agent to learn, which I'll show a bit later in the presentation with some of our experiment results. So a promising direction towards more robust RL is to learn a disentangled representation of observations. Disentanglement has been studied widely in the unsupervised learning literature, where disentanglement techniques aim to learn robust representations by separating distinct informative factors of variation into an image. So distinct informative factors of variation of the image into the unknown ground truth factors that generated the image. So, for example, here, using the disentanglement library from unsupervised learning, we have a set of different images with factors like the object shape, the object size, color, background color varying across these images. And disentanglement assumes that these independent ground truth factors of variation are used to generate the image through some function. And we want to take this image and learn a representation that separates out these factors of variation, essentially approximating the inverse of this function. So if an agent has a representation that's disentangled and it suddenly sees something new, like an object shape that it's never seen before, then only that one feature in the representation will change to something new. Everything else should remain values the agent is already familiar with and can still be relied upon for downstream tasks. However, in the disentanglement literature, it's been proven that it's theoretically impossible to learn ground truth factors of variation from IID data without some form of inductive bias or supervision. So recent approaches make use of non-IID images, such as assuming access to pairs of images with limited numbers of factors varying between the pairs. But non-IID data, which we need for disentanglement, is readily available in RL as the image evolves over time. So we propose an approach that uses this temporal structure of RL data to learn a disentangled representation. Our approach is called TED, which stands for Temporal Disentanglement, and it's an auxiliary task that can be applied to existing RL algorithms. So to explain how it works, I'm going to build up the architecture diagram, starting here with just a standard RL training update, where we take a transition containing the observation and next observation, pass these through the encoder using a target encoder for the stability for the next observation. The output of the encoder is the representation, which we denote Z, which is then used for the standard reinforcement learning update as per the chosen RL algorithm. So now adding the TED auxiliary loss to the diagram, which I'll go through in detail, but at first just at a high level, TED is designed to encourage the encoder to recover the temporal structure determined by observations at consecutive time steps, t and t plus 1, such that a classifier can discriminate between temporal and non-temporal pairs of representations. So in addition to the observations that we required for the standard RL training updates, we also need non-temporal observations. So we sample an observation from a different episode and a non-temporal observation from the same episode. And these representations are then used to create 3 different types of samples for the classifier. We have temporal samples consisting of the standard transition, non-temporal different episode samples, and non-temporal same episode samples. So these 3 types of samples are used to train a classifier to discriminate between temporal samples with a classification label of 1 and non-temporal samples with a classification label of 0, using a binary cross-entropy loss. And the structure of the classifier is based on permutation contrastive learning, which comes from the independent component analysis literature. It encourages disentanglement by ensuring that each feature of the representation is considered separately to the other features, which is denoted by the superscript I in the equation. And the B, K, and C here are the classifier parameters to be learned. So this encourages the encoder to not only uncover the temporal structure necessary for classification, but to do so by separating the factors of variation into distinct features in the representation, so that the temporal structure of each feature can be determined independently of the other features. So due to this structure, we're expecting the encoder to learn a disentangled representation and the classifier to approximate the distribution of samples. And the classifier is not required for execution, so it can be discarded after training. So one thing you probably notice is that we have 2 different types of non-temporal sample. We need the non-temporal different episode samples to encourage the encoder to disentangle factors that change each episode, like the colors in the example here. And we need the non-temporal same episode samples to disentangle the factors that are controlled by the agents, so change within an episode, such as the cart pole position here. Okay, so now moving on to some results. Our experiments are designed to evaluate whether TED allows zero-shot generalization to unseen values of an environment variable, and also to assess whether TED promotes faster adaptation after the change in the environment variables if generalization is not instant. So we evaluate our approach on settings where the agent must generalize to unseen values of variables with continued learning on the test environment. So we use a training environment with a subset of some environment variable, such as a subset of colors in the examples here. And then we switch to a test environment at the vertical dotted line in the graphs, and then continue training on this test environment, which has unseen values of the variable, such as unseen colors. So here we have the results for RAD and SPHERE as two different examples of base algorithms using the TED loss on the DeepMind control suite. And the paper has more results on more tasks for both of these algorithms as well. Our results show that TED, which is the blue line in the graphs, consistently improves generalization of the base RL algorithm, which is the orange line, in all the tasks, as well as outperforming state-of-the-art baselines. In many cases, we found that TED was able to achieve good zero-shot generalization performance, which can be seen at the vertical dotted line in the graphs, such as in the Walker task on the right. But where generalization is not instant, TED still recovers more quickly with continued training compared to the base algorithm and the baselines, such as in the cartpole task on the left. We also included domain randomization as a privileged baseline in green, which assumes that the test color set is known in advance, so the agent is trained on the two sets of colors together. And we found that in many tasks, TED was able to achieve better performance than domain randomization, such as in the cartpole task on the left, because it's more difficult to learn on this larger set of colors together. And we also evaluated the beta VAE disentanglement metric to measure the extent to which the learned representation is disentangled. And we showed that TED improves the disentanglement of the base algorithm, where a score of 1 is the highest for a fully disentangled representation. We also evaluated TED using the ProcGen suite with PPO as the base algorithm in this case, and using the jumper task as an example here, but again, there's more in the paper. Here, we're assessing generalization to unseen game levels, meaning we have unseen values of variables that are actually relevant to the optimal policy, unlike just colors in the previous experiments, which are irrelevant to the optimal policy. We now have things like the goal position or the layout of the level, as well as things like colors. So we're training on 100 levels of the hard difficulty. And again, we switch to a test environment at the vertical dotted line, which is 100 different hard levels, and we continue training on that test environment. And our results again show that TED improves the generalization performance of PPO, even when the unseen values include features that actually affect the optimal policy. Here you can see that we don't achieve zero-shot generalization, because when we're generalizing to unseen values of relevant features, the agent still has to learn something meaningful about these features to complete the task. But we still improve the zero-shot generalization on the vertical dotted line, as well as improving the adaptation performance of PPO. So altogether, our results show a variety of different tasks, with RAD, SPHERE, and PPO as different base algorithms using the TED loss, demonstrating the flexibility of our approach to improve generalization across different types of RL algorithms. So that's the end of the presentation, and I'm happy to take any questions or discuss any aspects of the work that people find interesting.